So if we want to add 28 plus 22, it's pretty simple. 8 plus 2 is 10, so we put the 0 down here, carry the 1. 1 plus 2 is 5. It's 50. Okay, simple enough. Now if we want to do that with binary, it actually works pretty much the same way. So we line up all of our columns, and so 28 in binary is 11100, 22 is 10110, so we've got that converted. We line up the columns, we just go column by column. So 0 plus 0 is 0. 0 plus 1 is 1. 1 plus 1 in binary is 2, but we don't have a 2 in binary, so we write it as 1, 0. So the same thing we did here with the 10. Here we do it the same thing. So we put a 0 down here and carry a 1. And that's how we write a 2. Here again, we've got 1 plus 0, which is 2. So we write that in binary again by carrying the 1 and putting the 0 down here. And then finally, 1 plus 1 is 3. And in binary, a 3 is 1, 1. And here we end up with the binary representation of 50. So the same algorithm works in any base, which is kind of cool. And so now if we want to build a circuit that does this for us, really it's actually a lot easier, I think, than regular arithmetic, because you only need to know a couple facts. And this is everything you need to know. And so if you can build a circuit that does all of this, then you can add a single column, because you've got the A and B, which is just the first number and the second number. And then you might also have this 1 that sort of carries in from the previous. So if you've got all that, then we should be able to add some numbers. So let's think about how we would build a circuit that kind of does this. And one way to do it is just kind of break down inputs and outputs. So we have the inputs A and B, and then we have these two outputs, which are the sum that you put down here at the bottom, and then the carry. I'll call this the carry bit, because you would carry that bit over to the next column. So if we look just at the case here where we've got two numbers that we're adding, so we haven't carried something in from a previous column, and we look just at the number that we're putting down at the bottom here, this actually looks a lot like an exclusive OR, right? Because if A or B is a 1, then this last bit here is a 1. If A or B is a 1, but not both. So we can actually start to build this, right? So we can have an exclusive OR gate here. This is how you draw an exclusive OR. And we have our A and our B coming in. And then coming out is going to be this right here. Now what about the second bit, the carry bit here? Well, this is also pretty simple, because it's always going to be 0 unless A and B are a 1. And so that's just an AND gate. So I can have an AND gate here. AND gate. And just take this same A and B input that we had over here, bring it into the AND gate, and this will be this bit here that we would potentially carry over into the next column. And so this actually is enough to add two numbers. This covers all of these cases here, because we have our A and our B input, our two inputs, and we have our two outputs here. This is this first output, and then this here is the second output. It gets a little bit more complicated now if we have a carry coming in from a previous column, because it's not enough to just be able to add two digits, because as soon as we get to this 1 plus 1, then we have to carry a 1 to the next column, and in the next column we have to deal with 3 numbers. So let's just kind of add this case where we have this carry that might be a 1. Well, in that case, if we look at the last column here, it's actually the inverse of the case here. So really what we want to do is we want to invert this output here whenever the carry bit is set. And a clever way of doing that is with another XOR gate, because when you XOR something with a 1, it will invert it. So if we have our carry coming in here, we send that into the XOR gate, and this will be the sum that we put at the bottom here, because what happens is if this is a 1, then a 0 XOR 1 is going to be 1. A 1 XOR a 1 is a 0. A 1 XOR a 1 again is a 0. And then here we have a 0 XOR a 1 is a 1. So this will give us this last column. Now for this first column, which is the carry bit that we might put into the next column, we've got these cases covered, right? Because if A and B is a 1, then we get our 1. And we even have this case covered here, because if a and b is a 1, then we have a 1 here as well. But what we don't have covered is these two cases here, where a or b is a 1 and we have this carry. And so what we can do is we can actually say, well, if we have the carry exclusive or a or b, we already have that exclusive or a and b. So if a or b is a 1 and we have the carry, then we want this 1. So we can actually just AND the a or b. So this is a or b we already have, and the carry bit is set. Then we get this 1 here. So now we have this case. Now we have these two cases covered by this output of this AND gate. Whoops, we want to bring the carry bit in there as well. And we have these two cases where it's 1 covered by this AND gate. And so really what we want to do is we want to say that this bit is going to be a 1 either time this condition or this condition is met. So we can use an OR gate. So this is an OR gate. This is an AND gate. This is an XOR. So you guys don't get confused here. And then this is the carry. And so this actually is what is called a full adder, because we have A and B, so we have two numbers that we're trying to add. We potentially have a carry from a previous addition, and then we get a sum out, which is the number we put here at the bottom, plus we get a carry that goes into the next column. And so with this sort of simple circuit, if we build one of these circuits for each column, we can add as large a number as we like, as long as we keep building as many of these circuits as we like. And so, for example, I've drawn up this diagram here, which shows that same circuit sort of replicated 4 times. And in this case, you have an A and a B coming in here, and the carry coming out goes into the carry of the next circuit. So this is sort of like, when you're actually doing the arithmetic here, you have a 1 plus a 1, you have a carry, it goes in as an input to the next addition. And so that carry comes into here, along with a new A and a new B, which is going to be the A and B for this column, for the second column. And then you have a sum coming out, which would be the number down here. And then you have that carry going over, which goes into the next column, plus the new A and the B for that column. Carry comes out and so forth. And so here I've drawn 4 of them, so we can add 2 4-bit numbers, but we could keep building more and more of these if we wanted to. So to actually build this, we can use some pretty simple components, because we have XOR gates, and these chips here actually implement XOR gates. And here is the data sheet for them. And so you can see from this data sheet, basically each of these chips has 4 XOR gates built onto it. And so, to build a 4-bit adder like I've drawn out here, you need 1, 2, 3, 4, 5, 6, 7, 8 XOR gates. So we have 2 of these chips. Each one has 4. We also need some AND gates. And so there's another chip that has AND gates. We need 8 of those. And so each of these chips has 4 AND gates, as you can see on the data sheet. So we got those. We also need some OR gates here. We just need 4 of those. So there's another chip that has 4 OR gates. So we got that. And then a couple other things that we need. We need a breadboard to build this on. So we're going to build this on this breadboard here. And for the inputs, I have these little dip switches. And so each of these has 4 little switches on it. And that'll let us set the 4, the A0, A1, A2, and A3 for the one number that we want to add, and then another one for the B0, 1, 2, and 3 for the other number that we want to add together. And then finally, a couple other things we need are some kind of outputs here. So we have our sums coming out here, and so I just have some little LEDs that'll light up for each of these digits, and I have 5 of them because there's 4 outputs plus the final carry, which is, because if you're adding 2 4-bit numbers, you might end up with a 5-bit output, so that last carry will have another LED for that. And then I'm just going to power it with a little bit of a little USB. This is just a standard USB charger that I've kind of hacked the end off of and just taken the red and black wires out of there, and that'll give us 5 volts. So I'm going to go ahead and start getting this thing built on this little breadboard here. And I'll just start by sticking this stuff onto the breadboard. Okay, at this point I've got everything on the board and all the chips are powered. So each of these chips has a VCC, which is the positive voltage, and then the ground. So each of those is connected for each of these chips. Everything's on the board. So I'll go ahead and just actually just wire up the first of the adders, and we can kind of play with that one first, and then we'll do the rest. Okay, so I've got the first stage of this wired up. I think we'll see. We'll power it up and see what happens. But so I'm using using two of the XOR gates on this chip, two of the AND gates on this chip, and then the OR gate is over here. So I've got some kind of wires running back and forth. But I guess as I do the additional bits, hopefully the wires will get a little shorter, so it'll all fit. But in any event, this is the sum of the first two bits over here, and this will be the carry. So let's get the power. I've got it already plugged in, so I'm going to just hook this up here and see what happens. And that's not good. Oh, I'm not done yet. Okay, now I think I'm done. I just had to hook up a couple extra connections here because the switches weren't fully wired in. Okay, so now we add power and everything is off because these first two bits are off. And if I toggle either of these on, hopefully, yes, we see 0 plus 1 equals 1. So this is a binary 0, 1. So this is the answer there. If we turn this off and turn the other one on, we see again 1 plus 0 also equals 1. That's good. And if we turn both of them on, we get 1 plus 1 equals 2. So it looks like this is working. So now I'll go ahead and just wire up, I'll actually wire up the remaining three adders, or the remaining three adders for the remaining 3 bits here. Okay, so I just finished this, so let's see if it works. I've been testing it as I go, but I haven't tested the whole thing all together. But let's see how it does. If we plug this in, we've got zeros and zeros, so we've got all zeros on the output there. So let's see if we want to do some arithmetic here with this. Let's imagine we want to add 10 plus 7 and get 17. So in binary, this is 10, this is 7. So we would add 0 and 1. And we get 1, and we add 1 and 1, and that's 2, so that's a 0, carry a 1. 1 and 1 again is 2, so 0, carry a 1. 1 and 1 again is 2, so that's a 1, 0 in binary. So this is what we would expect. So let's go ahead and give it a try. So 10 is 1, 0, 1, 0, so we can do 1, 0, 1, 0. And already you see the output is 1, 0, 1, 0 because we're adding that to 0. So 10 plus 0 is 0. So far, so good. And then 7, we can do 0, 1, 1, 1. So if we do 0, 1, 1, 1, there we go. We get 1, 0, 0, 0, 1. 1, 0, 0, 0, 1. So it looks like it's working.